All right, let's just dive right in. We're going to talk about physics today, but probably not in the way you're used to. We're moving beyond the equations and the tough homework problems. We're going to explore why physics is one of the most powerful tools you can possibly have. Seriously, no matter what you end up doing in life. It's a way of thinking. It's like having an analytical superpower.
First things first, let's tackle that classic question. You know the one. It gets asked in pretty much every physics classroom ever. When will I ever actually use this stuff? And you know what? It's a totally fair question. The answer, though, might surprise you. Because the truth is, you already use physics. All the time. Every single day.
For example, the next time you pull out your phone to use GPS, what do you think is happening there? That little device is crunching fundamental physics equations that connect speed, distance, and time just to figure out when you'll get there. Yep, that's all physics.
Or how about something even simpler, like heating up your lunch? That microwave is a little physics machine. It uses electromagnetic waves to make the water molecules in your food vibrate like crazy, and that vibration generates heat. The laws of physics are literally what's warming up your food.
And it goes way, way beyond that, into some really incredible areas. Physics is right at the heart of amazing medical technology like the MRI, magnetic resonance imaging. It uses these super powerful magnets and radio waves, concepts straight out of a physics textbook, to create these incredibly detailed images of the inside of the human body. It helps doctors find tumors and diagnose diseases. It's a lifesaver.
So here's our game plan for today. Here's how we're going to break down why physics is so important. First, we'll see how it's literally everywhere. Then, we'll open up the scientist toolkit. After that, we'll talk about what it means to hit the target with accuracy and precision. And finally, we'll pull it all together to show you how this becomes your own analytical superpower and why it really, truly matters.
Okay, first up, physics is everywhere. You see, the whole point of physics isn't just to describe a bunch of random things happening. It's this amazing quest to find the simple, fundamental rules that run the entire universe. We're talking from the tiniest subatomic particles to the biggest galaxies you can imagine. And this really gets to a core, beautiful idea in physics. It might seem like the universe is just this chaotic, complex mess, but underneath it all, there's an incredible order. Physicists have found that just a handful of laws, like the conservation of energy, can explain a huge range of what we see. So learning physics is kind of like learning the secret code that runs reality itself.
So how do scientists actually go about decoding all this? Well, they don't just guess. They use a very specific set of intellectual tools. And understanding these tools is so important because it's how we build knowledge. Let's take a look at the three big ones: models, theories, and laws.
All right, first in the toolkit is the model. The easiest way to think of a model is as a kind of mental picture, a simplified representation of something. A classic example you've probably seen is the planetary model of the atom, right? The one that shows electrons orbiting a nucleus, just like planets orbit the sun. Now, we can't actually see an atom that way, but this model, it's incredibly helpful for visualizing and understanding how it behaves. It's a really useful simplification. Okay, let's clear up something that trips a lot of people up: the difference between a scientific law and a theory. A law is a super concise description of a pattern we see in nature. It tells you what is going to happen. Think of something like F equals ma. It's a simple, powerful equation that just describes an action. A theory, on the other hand, is much bigger. It's a broad, complex explanation for why a whole group of things happens. So think of it this way. A law describes a single pattern, but a theory explains the entire framework behind it.
And that brings us to our next big idea. See, to test all these laws and theories, scientists have to take measurements, lots and lots of measurements. And there are two words here that are absolutely critical, but are often mixed up: accuracy and precision. To make this crystal clear, we're going to use a simple target analogy.
So here's the bottom line. Accuracy is all about correctness. How close are you to the real, true value? How close are you to the bullseye? Precision, on the other hand, is about consistency. How close are your repeated shots to each other? Are they all clustered together? And here's the key. You can definitely have one without the other. Let's see what that looks like. In this first target, the shots are just all over the place. They aren't grouped together, so that's low precision. And none of them are really close to the bullseye, so that's low accuracy too. This is pretty much the worst-case scenario in an experiment. Your results are both inconsistent and wrong.
Now, take a look at this one. See how all the shots are packed tightly together? That's high precision. Your measurements are super consistent. The problem? They're way off from the bullseye, so that's low accuracy.
This often tells you there's a systematic error, like your measuring tool is off. It's consistently wrong, but it's wrong in the exact same way every single time.
And here's the total opposite situation. The shots are scattered all over, so the precision is really low. But if you were to average all of them out, the center of that group is smack dab on the bullseye. This is high accuracy. It means your measurements are correct on average, but there's just a lot of random error or variation in there. And finally, this. This is the goal. This is what every scientist dreams of. All the shots are in a tight little cluster right in the center of the bullseye. This is high accuracy and high precision. Your measurements are both correct and they're repeatable. That gives you some serious confidence in your results.
So why did we just spend all that time on models and theories and targets? Because learning to think this way, systematically, logically, and critically, that is the real gift of studying physics. It honestly becomes your analytical superpower, and you can apply it in absolutely any field.
And this right here is the key takeaway. I mean, memorizing formulas is fine, but the real value of studying physics is developing the analytical skill to apply its principles to solve really complex problems. It literally trains your brain to break down a challenge, figure out the core principles at play, and then build a logical solution from the ground up. That skill is priceless.
And if you need proof, just look at how many other fields completely depend on it. Physics is the bedrock for chemistry, right? That's all about how atoms interact. It's the language of almost every kind of engineering, whether you're building a bridge or designing a computer chip. It's essential for architecture, for geology, and even for medicine, with things like X-rays and MRIs. Physics isn't some subject in a bubble. It's the foundation that so much of modern science and technology is built on.
So let's bring this all home. Why does any of this really matter? It matters because studying physics fundamentally changes how you see the world. It gives you the tools to look past the surface of things and understand the deep mechanisms that are running underneath everything.
And that, ultimately, is the superpower. It's not just about knowing a bunch of facts. It's about developing a powerful new way of thinking. The problem-solving skills you build in a physics class will make you a better thinker, a better analyst, and a better learner, no matter what career you choose. It just makes everything else make more sense.
So, I'll leave you with a question to think about. Now that you have a little glimpse into the physicist's toolkit, this search for simple laws, the use of models, and the strive for accuracy and precision, what hidden patterns can you start to see in your own world? Just look around.